Hey everyone, sorry the video cut off. My parents were calling me even though I told them that I'd be busy, but they have to do that. But anyways, we were working at number 6 and I had just gotten to figuring out the moles of our initial reactants and we constructed the ice table. So I'll go over that again. Um, so basically, to construct an ice table, it is used to figure out the equilibrium concentrations. Um, and that will also help us figure out the equilibrium constant as well. But in this question, it is asking for the equilibrium concentration of Ml2. Um, so to begin with the ice table, I usually call it rice table because we always have to include the reaction, which is written here, and we made sure that it was balanced out. And then I is the initial concentrations of the compounds, and in this case, for M2 plus, we figured out right here that both of our reactants are have a concentration of 0.001 moles, and we have a 0 initial concentration for Ml2 because it is a product. It still hasn't been formed yet. And then we reach to the second part, which is C, and that means change. And basically, that's how the reaction proceeds and the degree of which these how they form or degrade. In this case, 2 plus has a minus x, and that is because it has only a coefficient of 1, so it's just minus x. So x is a variable to tell us like how much, and that's what we're trying to figure out right here for our equilibrium concentration. And then 2L would actually be minus 2x because it has a coefficient of 2. And then for Ml2, it has positive X, and that's because it is being formed. The reactants are being used to make product, correct? So then we basically form these two expressions in our equilibrium row. And so we have 0.001 minus x, 0.001 minus 2x for L, and we have x because for Ml2 because it's just that's our variable. It's positive. And then in the problem, it's given that the concentration of L is found to be 0.01 at equilibrium. So let's first write out that our total volume is 10 plus 10 of our reactants, which will give us 20 milliliters. So this will help us figure out the moles of L, since we already have, at equilibrium, since we have the concentration of L. So in this case, it would be 0.0100 mole per liter times 20 milliliters times 1 L over 10,000. And that will give us 0.0002 moles. So that will mean 0.001 minus 2x is equal to 0.002 moles. So what does that mean for Ml2 plus? Because that's what we're trying to find, right? Well, remember that Ml2 plus is x. So basically, in this problem, what we're just gonna have to find is the value of x in this equation. So x is equal to 0.001 minus 0.002 over 2. And that will give us 0.0004 moles and 20 mLs for ml2, right? But that doesn't give us the moles because remember that's what we're trying to figure out. I mean, that gives us the moles, but we're trying to figure out the concentration. So basically, all you're gonna have to do is multiply 0.0004 moles over 20 ml, which is basically the expression right here, times 1 liter over 1,000 milliliters, and that will be 0.02 moles per liter. So that gives us how to do the ice table for one of these questions. So let's move on to the next question. So it's saying in number 7, the equilibrium constant Kc for the reaction is 49 at 230 degrees Celsius. What does that mean for us? What we're trying to figure out? The concentration of PaCl3 when equilibrium has been established. So we already figured out that 0.7 moles of PaCl3 is added to 0.7 moles of Cl2. Okay. And we already have the Kc right here. Okay, perfect. So our equilibrium equation, we'll start out with that. Kc is equal to 5 and KH is equal to 49. And the initial concentrations for PCl3 and Cl2 are both the same. They're 0.7, so we already know that. And we just have to figure out in moles since it's already added into 1 liter. So that will be 0.7 for both at initial. So let's make our ice table. I'll do that here. So we have PCl3, Cl2, and PCl5. So we have 0.7 here, 0.7 here, and we have 0 here. Again, similar to what we did before, the change will be minus x, and plus x. And our equilibrium expression would be 0.7 minus x for both the reactants and x. So that was pretty simple to do, right? In this case, what that means is 49 equals x, because we're basically, what we're doing right here is we're filling this expression, okay? So what that means is x, which symbolizes PCl5 at equilibrium, over 0.7 minus x squared, right? Because they're both the same. And in this type of an expression, what we'll have to do is switch it to, I believe it's the quadratic equation, I believe. But in order to figure out what our x is, okay? So what we have to do is x is equal to 49, right, times and basically what we did here is we expanded this, right? And that will help us figure out what x is. And to make this equal to 0, we'll have to do 49x squared is equal to, minus 69.6 x plus 24.01 is equal to 0. And x here is then when we use the quadratic equation, x is equal to negative b plus or minus the square root of 2b minus 4ac over 2a. And then that will just be 69.6 plus or minus, sorry, I made a mistake right here. This is supposed to be b squared. Minus 4 times 49 times 24.01 all over 2 times 49. So if we solve this, we will only get one positive answer, and that will be 0.59. So to figure out the final concentration of PCl3, because that is what the question is asking for, we just found out that this is X, right? So PCl3 is equal to 0.7 minus X at equilibrium, correct? And we just figured out X, so 0.7 minus 0.59 is equal to 0.11. And that is the answer. I hope that makes sense. Okay, moving on to number 8. Magnesium hydroxide, it is asking what happens to the hydroxide ion concentration if another 10 grams of magnesium hydroxide are now added to the mixture. So basically, this is something where you have to just look at the reaction, and it's saying 100 grams of magnesium hydroxide is added to 1 liter of water and equilibrium is established. So this basically just states that, okay, here we are at equilibrium. What happens to the solution if another 10 grams of magnesium hydroxide is added to the mixture? So this is something that talks about Le Chatelier's principle, and it's basically a principle that discusses the dynamics of equilibrium. However, one thing that Le Chatelier says is that solids and pure liquids do not affect the equilibrium, like we talked about before. So in this case, no matter how much you take out or how much you put in to a solid, it will not affect the reaction at all or the equilibrium. So nothing's gonna happen. It will remain um, the same. Like it will not be unchanged. So that's just a conceptual question that you guys need to know, because equilibrium is based on a lot of conceptual stuff, and it's one thing to know the calculations, and it's another thing to know the theory behind it. Okay, moving on. Methanol can be synthesized by combining carbon monoxide and hydrogen. Um, so it gives us a reaction. Um, it's saying a reaction vessel contains these compounds at equilibrium. Will the partial pressure of CO increase or decrease when equilibrium is reestablished after decreasing the temperature by 45 degrees? So, let me write the reaction down. And here we see that the forward reaction, which is right here, is exothermic, because here is a negative sign and it yields negative 90.7 kilojoules. So will the partial pressure of carbon monoxide increase or decrease when equilibrium is established after decreasing the temperature? So in this case, we're removing heat, correct? So another way to write this would be plus heat. So if we remove some heat from here, that means that the reaction will want to move forward to make up for that loss of heat here, um, and to reestablish equilibrium. So the partial pressure of CH3OH will increase, whereas the partial pressure of carbon monoxide and hydrogen will decrease, because the forward reaction um, will be favored. So the answer is decrease. It will decrease. Okay, moving on. So stearic acid, nature's most common fatty acid, dimerizes when dissolved in hexane. And it gives us this really big compound reaction. The equilibrium constant for the reaction at 28 degrees Celsius is 2900. Estimate the equilibrium constant at 38 degrees Celsius. And it also gives us the delta H. So there is another equation for this kind of a question, and that is ln K2 over K1 is equal to negative delta H over R, and that multiplied by T2 minus T1. So that is an important equation. So K2 is the equilibrium constant at temperature T2, and K1 is the equilibrium constant at temperature T1, and delta H is the enthalpy change. R here is the constant, 8.314, and so we can move forward. So let's look here. The T1 is right here. It's 28 plus 273, which is equal to 301 K. So T2 is asking at 38 degrees Celsius, and that is 38 plus 273, which is 311 kelvins. Remember that R is 8.314 joules per mole. Okay, so in this case, what we're going to have to do is change our delta H to joules, because we need to have the same units, and that will give us negative 172,000 joules. Okay, so then from here it's pretty much plug and chug, because what we're trying to figure out is K2. So ln K2 over 2900 right here is equal to negative 172,000. I mean, negative 172,000 over 8.314 times 1 over 311 minus 1 over 301. And then ln, to simplify that, is equal to negative 2.209. And then to figure that even more, we can raise this both to figure out K2 to get rid of the ln. So in this case, K2 will be 318. Okay, pretty simple. Just make sure that you know this equation. Cool? Okay, next we will talk about acids, okay? So just a reminder of these strong acids that we should all know by memory. We have HCl, HI, HBr, HNO3, H2SO4, and HClO4. So please commit this to memory. You will be asked, if not in this class, many other classes. So the question is asking which of the following is the strongest acid. So we already know we can take this out. So one thing I want to talk about hydrogen fluoride is that yeah, it is a halogen, and as you can see in this list, all the other halogens are considered strong acids. But the reason that HF is a weak acid is because fluorine is the most electronegative atom, correct? And that means that it will not readily give up that H because it's so electronegative, and that's what goes behind why HF is a weak acid. So if we just go through this other list, we'll find out that HI is the answer. Okay. And then number 12 is asking which of the following acids have the lowest and highest pH. Most importantly thing to remember is that the pKa value does not depend on molarity, so it does not matter. The molarity in this case is negligent. It is actually dependent on the structural factors of the molecules in the acid and the solvent. Those two factors affect the pK values of acids. So the lower the pKa value, the lower the pH value. Okay? So in this case, when we look at our list, we'll find that HBO has the highest and HST has the lowest. Okay? So this one will be the most acidic, and this one will be the most basic. Okay? And meaning that the acidic will have the lower pH and the more basic will have the higher pH. Okay? I hope that helps. Another question, what is the pOH of a 0.0250 molar HI solution? Okay, so one thing to keep in mind about strong acids, since HI is a strong acid, as we just talked about, it will only dissociate into H plus and I minus, correct? So H plus, in this case, is equal to the concentration. And that makes this pretty easy because we already figured out the H plus, and pH is the negative log of H plus. And that would mean negative log of 0.250, and that would be 1.6. Another way to think about that is since we figured out the pH right now, we know that pOH plus pH is equal to 14. pOH, to figure out pOH, it's the negative log of the base. Right? So in this case, all we have to do to figure out the pOH is 14 minus 1.6, and that would give us 12.4. Okay, so our answer is 12.4. Okay, moving on. This next question is asking the hydrated aluminum 3 plus ion is a weak acid in water. What are the products of its reaction with H2O? So, since aluminum chloride is added to water, it gets hydrolyzed because Al3 plus is a highly charged ion. You can see the 3 plus, and it's small, so it attracts water molecules that bind to it um, through covalent bonds, and the Al3 plus is able to attract the lone pair of electrons of the OH, so in the water molecule. So it splits into OH and H plus, and that would mean that our final reaction would be AlH2O 3 plus 6 5 OH plus H plus. Okay, another way to think about it is, since it said it's a weak acid, right? So that means we have the conjugation idea. So since this would be an acid, it must form a base. It's conjugate base when it's dissolved with water. So then that's how you see the OH, and in this case, it lost one of its waters. And then H2O is a base in this problem, and it becomes a conjugate acid in the products. Okay, remember H2O is a molecule that can both be acidic and and basic. Okay. Okay, so number 15, select the pair of substances that is not a conjugate acid-base pair. So remember what I was just saying about acid and conjugate bases? The only way you can have an acid and a conjugate base is if you lost a hydrogen. So in this case, we have H3O plus and H2O. H3O plus here is considered the acid, and this is a base. That makes sense because it lost a hydrogen. It went from 3 hydrogens to 2 hydrogens. So an acid base, a conjugate acid base pair is when you lose or you gain only one hydrogen. Okay, so that would mean the first one is correct, and the second pair is saying HNO2 and NO2 minus. It looks correct because it only lost one hydrogen. So this would be the acid and this would be the base, okay? Because it lost the hydrogen. And then H2SO4 and HSO4 minus. Now, H2SO4 is a diprotic acid, meaning it has 2 hydrogens. So if I have 2 hydrogens, my conjugate base would be HSO4 minus. And then if we were to say that this is an acid, its conjugate base would be SO4 minus. So this problem, it's wrong because the conjugate base for H2SO4 is HSO4 minus. It only loses one hydrogen. So yeah, this would be the answer. And then just to make sure the rest of the questions make sense, because we have H2S and S2 minus, so lost one hydrogen, and same thing for the last one. Okay? Perfect. Okay. So, a 0.05 molar solution of the weak acid HA has a concentration of H3O plus 3.77 times 10 to the negative 4. What is the Ka for the acid? Okay, so let us write the reaction out. So we have weak acid HA. So that would mean HA plus H2O gives us A minus, which is the conjugate base of HA, which is our weak acid, plus H3O plus. Remember, conjugate bases and acids only work for weak acids and bases because strong acids and bases completely dissociate, right? So this is where we begin to write out um, our ice tables for acids, okay? Um, so we have a concentration of 0.05 molar for HA, and remember, since these are products for A minus and H3O plus, we have 0. And we don't include H2O because it is a pure liquid. And so this would be minus X, this would be positive X, and that would mean 0.050 minus X, X and X. Okay, and so now we're trying to figure out, we know that we already know our X value because our X value for a weak acid is the concentration of H plus or H3O plus. And that is already given to us right here. Okay, so X is equal to 3.77 times 10 to the negative 4. In that case, Ka is A minus over HA. And I'll keep on writing here, and that means it is 3.77 times 10 to the negative 4 times 3.77 times 10 to the negative 4, because remember that is our values at equilibrium for the products, over 0.05 minus X. But remember, I'm sure Dr. Jing went over this, we neglect the X in here because it is a small value. So our answer would be 2.84 times 10 to the negative X. This is our Ka value. Okay? Perfect. So let's move on. So phosphoric acid, H3PO4, is a triprotic acid. So tri means 3, protic means hydrogens, because those are the ones that become protons, not protons, positively charged. And so it's saying it gives us the Ka values for all 3 hydrogens, and it's saying what is the value of Kb for hydrogen phosphate ion HPO4 minus. Okay. So the dissociation steps for phosphoric acid is as follows. We start out with H3PO4, and that gives us H2PO4 minus plus H plus, and that will be given as Ka1. Then we have H2PO4 minus, that will give us HPO4 2 minus plus H plus. That will give us Ka2. Then we go HPO4 2 minus, that will give us PO4, oops, PO4 3 minus plus H plus, and that will be Ka3. Okay, so like I said, a conjugate acid-base um, pair differ by a proton, only one proton. So the HPO4 2 minus, which is right here, is a conjugate base of H2PO4. See right here, if we were to think that this is the acid, then this would be the base. This right here would be the base. Okay? So Ka of a conjugate acid and Kb of a conjugate base are given as such. 10, negative 14. Thus, the Kb for HPO4 2 minus is Ka2 times Kb, which, and 10 to the negative 14. That means Kb is 10 to the negative 14 over 6.3 times 10 to the negative 8. And that will give us 1.6 times 10 to the negative 7. Cool. Okay? Just make sure you understand the idea of conjugate acid-base pairs and how to figure out, like, for acids that are diprotic or triprotic, how to deal with them as well. Okay? So number 18 talks about a solution is prepared by adding 0.1 moles of sodium sulfide Na2S to 1 liter of water. Which statement about the solution is correct? So the correct answer should be A, because the solution is basic. Na2S is a weak acid. It's the salt of NaOH plus H2S will give us Na2S plus H2O, right? So this is a strong acid base, NaOH, right? And this is a strong acid, and they'll give us a salt, Na2S, okay? And this will be a base. Okay. So that's another topic about bases, salts that are formed from base, strong bases, strong acids, and it wouldn't be neutral because actually, let me think about it for a second. So NaOH is a strong acid, strong base, and H2S is a weak acid. I'm sorry. This is a weak acid. Okay? And this is a strong acid. And when you have a strong acid, strong base. Wow, I keep on messing that up. When you have a strong base or acid, it will dissociate completely, so it'll give a neutral value to the salt. But when you have a weak acid, it will dissociate into its conjugate base. So this will be the conjugate base salt, and that will give you a solution that is basic. Okay? That makes more sense. Okay, so the next question is talking about bases, a Lewis base. Okay, so we have three um, acid base definitions. The first one is the Arrhenius. Okay, and the Arrhenius says that acids are H donors and bases are OH donors. Then we have the Bronsted-Lowry. And it says that acids are proton donors, so they lose H plus. Bases are proton acceptors. They gain H plus. Okay, so an example for an Arrhenius acid would be HCl. Okay, it has a hydrogen to donate. An example for an Arrhenius base is NaOH. It has an OH to donate. For the Bronsted-Lowry acid, we have HNO3. It can lose an H plus. Bases for Bronsted-Lowry include NH3 because it can accept and gain H pluses. And then the last one would be a Lewis base or acid. So an acid accepts electron pairs. A base donates electron pairs. Okay, so in this question, we have which of the following is a Lewis base? So something that can donate electron pairs. In this problem, it'd be Cl minus because it has that negative extra pair of electrons that it can readily donate. BCl3 is neutral. All the other species are positively charged, so they are actually Lewis acids. So Cl minus is the only one that fits a Lewis base. Okay. Okay. So number 20. Which of the following pairs of 0.1 molar solutions when mixed will produce a buffer solution? So remember, a buffer solution is one which resists changes in pH when small quantities of an acid or a base are added to it. So, and it has to be a small change. It can't be something drastic. So in this case, an acidic buffer solution um, is one that has a pH that's less than 7. And they are made from weak acids and it's salt. Okay, weak acid plus salt. Okay, so in this case, the only option that is correct is the 50 mils of aqueous CH3COOH and it's salt. So think of it like a conjugate base and its acid. And the other problems, none of them make sense. You can't have a weak acid right here and a strong acid that will not be a buffer. And the next one, you don't want to use strong bases or acids in buffers, okay? So that will take out this and this, as well as this. So the only one that makes sense is the last one. You don't want to use strong bases and acids in buffers. That will completely defeat the purpose because they do drastic changes in the pH. Okay. So for 21, it's asking a buffer is prepared by adding 0.5 moles of solid sodium hydroxide to 1 liter of 1 molar acetic acid. What is the pH of the buffer? Okay, so we know the number of moles of NaOH is 0.5, and of the weak acid, which is acetic acid, we have 1 liter times 1 molar, and that is equal to 1 mole. So that we can create the reaction of the buffer. So here we have 0.5 and 0.5 and 0.5 here. So the number of moles of HA left, or the acetic acid, would be 1 minus 0.5 moles. So that's what we figured out right here. And that would give us 0.5 moles of acetic acid. So the pH from the Henderson-Hasselbalch equation would be pH equals pKa plus log of base over acid, and that would be mean the pH is equal to the pKa because log of 1, or yeah, log of 1 is 0. Okay, so then the pH is equal to the pK, and that's when you know that something is at a buffer, like when the pH is equal to the pKa. So again, since we here are using 0.5 moles of NaOH, 0.5 moles of acetic acid will be used, and that will mean that we'll have 0.5 moles of acetic acid left. And that's what we put into consideration when doing the Henderson-Hasselbalch equation. Okay, so the last question, also please make sure you understand the Henderson-Hasselbalch equation. What happens when you add acetic acid, or what would happen if you, like, things you should think about is like, what would happen if I added in an acid? Because if you add in, like, let's say 1 mole of acid, that would mean that you'd have to take away 1 mole of base. It's not like it's because this is a buffer, so you have to account for every change that you make. So that's something that's really important to think about. Okay, so for 22, when a weak acid is titrated with a strong base, the pH is at the equivalence point, should be uh, greater than 7, because a weak acid will give us a conjugate base, and a strong base will just completely dissociate, so it won't give us anything. So that will leave us with the conjugate base, and that would be greater than 7. Okay, so that is the end of my solutions. I hope you guys understood some things better, and I will upload this along with the problems for you guys to take a look at. And please, 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 if you have any questions, email me and I'll be happy to help. Good luck, and I hope everyone is staying safe.